All right, as you know, there's a midterm this week on Friday. It's going to be right here in the classroom. It's going to take just the 50 minutes that we have for lectures. You won't use anything other than a formula sheet that I hand you and what's in your brain. No text, no notes. You don't need any electronic devices, so we won't be using those. Like I've already announced, there will be 2 review sessions that the TAs will hold Tuesday and Thursday. They're not in this room. They're in the room around the corner, 004, from 4:30 to 5:30. And they're not going to cover the same thing. They'll each cover different things. It's just a review. The exam, there have been some questions about, will the exam, for example, have questions about the labs? Actually, no. It'll be on the lecture material, the types of things you covered in your problem sets. The exam won't be an exam that asks you to prove things. Like, for example, in your homeworks, you've proven some properties of the Fourier transform. It's not going to have that style of question. It'll be more applying what you've learned. It won't be so much just regurgitating knowledge. It'll be using what you've learned for some problems. Okay, so that's all for the exam. Yeah, go ahead. Yes. We'll post the answers probably today or something for that one, for the 3rd problem set. Okay. So today we're going to start this discussion by mentioning that the different flavors of the Fourier transform that we've seen so far can actually be understood in a unified context. So that's going to be one of the points of today's lecture. Here I've written a chart of 4 different Fourier things that we've learned. We've learned the Fourier series. We've learned the Fourier transform. So this top row is the 2 Fourier series that we've discussed. One for continuous time, one for discrete time. Okay. We've also then discussed the Fourier transform for continuous time and discrete time. Now let's just kind of look and compare these because it would be nice to understand them in sort of one context. Why do we have 4? Can we just think of one? Turns out we can if we interpret it the right way. But let's first notice some important aspects of this. So I'm going to write some time domain properties in green and frequency domain in red. Okay, so to begin with, clearly this first column here is continuous in the time domain. That's hence the name. Continuous time Fourier series, continuous time Fourier transform. And this column is discrete in the time domain. Now, in the frequency domain, we notice something interesting for the discrete time Fourier series and the discrete time Fourier transform. For both of those, we have that it's actually periodic in frequency. You remember we noticed it was periodic because of this property of aliasing, right? And that only happened in discrete time that we had aliasing, so that the frequencies would be periodic. Okay, now along these rows, we have that for using the Fourier series, that's the top row. In time, you should be dealing with a periodic signal. That's what the Fourier series is defined for, periodic signals. All right, and the Fourier transform, on the other hand, does not require that it be periodic. The lower row. Now, in frequency, we notice that the Fourier series gives us back a list of coefficients. In other words, in frequency, it's discrete. All right, whereas the Fourier transform is not discrete in frequency. It gives us a function of f. So this is continuous. So we see that this notion of duality is appearing again. Look that our properties are the same down the columns and across the rows. In other words, if either one is discrete, then its complementary domain is periodic. Same thing over here. In time, we're periodic, and that causes frequencies to be discrete. Here, in time, we're discrete, and that causes the frequency domain to be periodic. So these always go together with these transforms. Okay? So if it's aperiodic, not periodic, then it's going to be continuous in, here, let me go this way. If it's aperiodic in time, it's going to be continuous in the frequency domain, not discrete. Okay. One other thing is that the Fourier series is defined to be used on finite power signals. So they're periodic. Periodic signals will not have finite energy, but it should have finite power at least. The only way it's going to have infinite power is if it has some vertical asymptotes. Okay, we haven't really cared about those kind of signals. And similarly, this Fourier transform is well defined for signals of finite energy. So if here you can have a signal that doesn't have any vertical asymptotes and is still infinite energy, just a signal that doesn't decay fast enough with time. When you calculate its energy, you integrate overall time, and it could be infinite. And that wouldn't be handled well with the Fourier transform. It should be finite energy. Although we're going to see that, in fact, we have, for some cases, we have a way of tricking the math and actually handling periodic signals with this Fourier transform. So I'm going to write that this is actually the most general. If you have the right way of interpreting everything in this context, then really understanding the continuous time Fourier transform allows you to understand everything else. Okay, but I say it's most general, and then you could look at this and say, no, it's not most general, because periodic signals can't be handled technically through this continuous time Fourier transform, right? They wouldn't have finite energy. Okay, that's true, but we have a trick. So can anyone think of the trick that we've introduced here, the mathematical trick that we've said, well, this isn't really precise mathematics. It's a function that's not really a function, but we're willing to use it. The delta function. The delta function is going to allow us to actually make this continuous time Fourier transform the most general of all four, okay, by using the delta function. All right. One more thing I should mention here is that the DFT is this corner. So the DFT, what you're using in MATLAB, it's implemented with the FFT algorithm. That's this case of discrete frequency and discrete in time. And remember that we can interpret it. You always have like a finite window of data. You apply a DFT. And the best interpretation should be that this is like a Fourier series on the periodic extension of that data. That's what the DFT is doing. Okay. So we're going to talk about the delta function a little bit more, and then come back to seeing how can all of these be understood as continuous time Fourier transform. So we didn't talk about all of the properties of the delta function that we wanted to. So let's first finish that up. Oops. All right. In particular, we said what the delta function is defined, how it's defined under the integral for infinite integrals. But what about if the limits of the integral are not negative infinity to infinity? How do we handle that with the delta function? So what if we integrate over some set A. So think of that over from some number to some other number. Okay, not infinity. Delta t, f some other function of t, dt. Okay, so how do we handle this integral? Well, I think intuitively you might expect that if the delta function occurs inside that integral, then it's going to be the same as integrating from negative infinity to infinity. If the delta function's outside that interval, then it's 0. Okay, that might already match your intuition. But in fact, we can get that by simply saying whenever you integrate over some set that's bounded, then that's the same as integrating from negative infinity to infinity and bringing in an indicator function. So we would have this, and then we would have an indicator function on the set A. That means this is a 1 if and only if t is in A. It's a 0 otherwise. Okay, so you can see these are the same thing. That's one way of always taking an integral, taking any integral and making it an integral from negative infinity to infinity. Just bring this indicator function in. Okay, so now we already have a rule for how to do this integral. And what is it? Well, now we should look at this part together as the function that we're multiplying by delta. And we know that we should get f of 0 indicator. We should just get that evaluated at 0, right? Okay, which means I would like to make this more general. Let me just modify this example. Rather than having the delta function occur at 0, I'm going to make it a delta of t minus some t naught. So it's a shifted delta occurring at t naught. So then I'll change this one too. Okay, so we know the rule for shifting. That is, we just evaluate this function at t naught. Okay, which is going to equal f of t naught if t naught is in A, and f of and 0 if t naught is not in A. Okay, so it's exactly what we said the intuition should tell us. If the delta function occurred in the set A, then you just treat it, it's an integral is an integral, it doesn't matter. But if it's outside of A, then the integral is not hitting your delta function. Okay, so of course we had it's undefined if t naught lands right on the boundary of A, because we had a condition for shifting that had to be continuous at t naught. Okay, and notice that this function here would be discontinuous if at t naught if the indicator function, if that was the boundary of the indicator function. Okay. Great. I think that's enough about that. Let's also look at another example of delta function. This is an interesting case to look at. What is the integral from 0 to t of delta tau d tau? Okay. Well, because we know the above, we know that only this delta is occurring at time 0. So only if that interval includes, whoops, I want negative infinity here. So only if that interval includes 0 is this delta function going to be evaluated. And that means it's going to be 1. It's going to be 1 when t is greater than 0. And 0, t is less than 0. And it's undefined when t actually equals 0. We don't care too much about that. So this is the unit step function. Okay? Well, that's nice because we know integration and differentiation are inverses of each other. So this is like saying one way to think of the delta function is that delta of t equals the derivative of the unit step function. All right, I know some people in this class already had that interpretation from other classes. If you want a derivative of a jump, that's what the delta function is. Right? All right. All right. Someone have some idea of what the energy of the delta function should be? How do we calculate the energy, or what is it? Any guess? 1. That's a great guess. It's not true. I'm always baiting you for the answer I want you to say, which is not the right answer. Okay, so it's not 1, but it seems like it might be 1, because when you integrate the delta function, you get 1. Okay, but if you try to calculate such a thing by taking the magnitude squared of the delta function, the problem is we don't have a way of handling two delta functions multiplied together. That's just, we should consider that an undefined thing. And we have reason to, you'll learn later, reasons to understand that this is actually infinity. The energy of the delta function is actually infinity. Okay. You could, yes? That'd be great. So you could do that. You're saying, why not look at it like this, delta t, and one of these is your f, right? Then you would plug in 0 to the delta, and the answer should be delta at 0, which is like, okay, maybe you think of it as infinity. Okay, good idea. I mean, you could argue that this should be infinity because you could look at the approximating functions that we use to motivate the delta function. We said that we had these rect approximations, which were the delta, these things of width, capital delta, right, and height, 1 over capital delta. Of course, the energy of this thing, if we calculate the energy of this for any delta, we get, you can try it out, you'll get a 1 over delta. Okay, because it's a rect and it's got height 1 over delta, but then you square it, you integrate, you just get 1 over delta. And this goes to infinity as delta goes to 0. Okay, so there's another argument why maybe it's infinity, but the bottom line is don't try multiplying delta functions. Okay, we're not going to have a good definition for that. All right. Of course, for convolution is the only way where I guess technically we're allowing the multiplication of delta functions, because we have a rule that delta function, a shifted delta function convolved with anything. Let's make that x of t. Convolved with x of t, we've already checked that that's always going to be the same thing, x, but just with the same time shift, t minus t naught. So we have that property. Okay. And so if we have a signal that has delta functions in it, let's say like this, delta t, let's say our signal x of t actually has some delta functions. I'll just make up something, t minus 1. Okay, so that's our x of t. Well, then we could use the same rule and say this should be 3 delta t minus t naught minus 1. Okay, so that's okay, even though technically if you wrote out this integral, you're multiplying two delta functions. Okay, we allow that sort of thing because we know that we have this rule. The delta function is sort of the identity impulse response. Okay, so it's the identity for convolution. So, this kind of thing is allowed, even though if you tried to do this out by hand with the integral, you'd see multiplication of two delta functions. Okay, great. I think I have something else here. All right. So the next thing we want to do is try taking a Fourier transform of a delta function. All right. And here's where it starts getting very useful. So what if we want take just a simple shifted delta function, t minus t naught, okay, and take its Fourier transform? How do we do this? Well, we could plug in the integral for the Fourier transform. So here's the definition. And then we use sifting, right? So this delta function occurs at time t naught. So I'm just going to get equals e to the minus I 2 pi f t naught. Okay, now this is a function of f, right? The Fourier transform is a function of f. T naught's just some number. So maybe it's more intuitive to put the f at the end. So there we have some constant, which is negative I 2 pi t naught, and this times f. Okay, so in the frequency domain, this is a complex exponential function. All right, that's the frequency domain for a delta function. Great. Now let's do this in reverse as well. Let's say if we have, because this integral should be just as easy if we do an inverse Fourier transform, okay, which will give us a reverse relationship. So what if we have delta t of f minus some, so a delta occurring in the frequency domain at some location f naught. Okay, and we want to know what time domain signal does that correspond to. Well, to calculate this, we can do an inverse Fourier transform. Of course, here what we're going to get is the inverse Fourier transform looks almost the same. Plug in our frequency domain signal, and we're just missing the negative up here. We integrate with respect to f, and again we use sifting, right? And we see that this gives us e to the I 2 pi f naught t. So that's a time domain signal. Again, it's a complex exponential in time at frequency f naught. It's the simplest sinusoid we deal with, right? Because we're always dealing with complex exponentials. So actually, let me change a battery, because otherwise the sound's not going to work here. Great. So in this class, we're dealing with sinusoids that are actually complex exponentials. So we're saying a complex exponential in time is a delta function in frequency. The location, it's very intuitive. The location of that delta function is exactly the frequency of the sinusoid. Okay? So to be maybe even more clear, what if we have a signal sine of t? Okay, there's a very simple real sinusoid. I want to know, what is the Fourier transform of this? All right. Now, to begin with, you might say, gosh, this isn't quite fair, because our Fourier transform is not made for periodic signals, right? Isn't that what I emphasized at the beginning of this lecture? The Fourier transform is not for periodic signals. The Fourier series is, all right? But we just derived, using the delta function, a relationship that here's a periodic signal that has a continuous time Fourier transform. It's a delta function. So these delta functions allow us to cheat the system. By using a delta function, we can actually represent a periodic signal in time using the Fourier transform. How do we know? Because we just checked it. We put a delta function in frequency, and we saw that that gives us a periodic function of time. Okay. Similarly, if we put a delta function in time, we get a periodic signal in frequency. Okay. So let's try this. We have a sinusoid. We know that we should be using the Fourier series, but instead we're going to use the Fourier transform using this relationship we just derived. Well, first thing, let's say this sine can be rewritten as 1 over 2i e to the it minus e to the negative it. Okay? And we can rewrite this one more time in the form that's a little more natural. Let's split this into two here. E to the I 2 pi, 1 over 2 pi t minus 1 over 2I e to the negative I 2 pi, 1 over 2 pi t. Okay, now it looks exactly like the formula we've derived here. We have a sum of two things. We can use linearity to handle them both separately. And we say that is exactly 1 over 2I. And the Fourier transform of this complex exponential we know is just a delta function, f minus 1 over 2 pi. So you see that we now have taken a periodic signal, a simple one, sine, and we've said, we have a Fourier transform of that. It's made up of delta functions. Because sine is a real sinusoid, it has a positive frequency and a negative frequency component. Okay, here are the frequencies. This sinusoid has a frequency of 1 over 2 pi, and it turns out the delta functions are going to occur at 1 over 2 pi and negative 1 over 2 pi for this. Okay? Cosine would be similar, but the constants would be different. Let's take an example from your first problem set. All right. Okay, you were given a signal. It was x of t equaled e to the negative I pi t plus e to the 2, 1 plus I pi t. All right, and you were asked, what is the period? Give us the Fourier series coefficients. Okay, Fourier series would be the natural thing to do here because it is periodic. We could find the period by just saying the period of this guy alone would be 2 because, well, we just know it would have to, t would have to equal 2 for this to have completed a cycle. Now here, the period is 1. And when you add two signals together of different periods, then it's the least common multiple that's the period of the sum. So 2 is the period of this entire thing. All right, t equals 2. Now, you then could calculate the coefficients using the Fourier series integral. I want to show you another method, which maybe you saw in the solutions. We could rewrite this in a form that looks like the Fourier series analysis equations. I'm just going to rewrite it as e to the I 2 pi, and then I'm going to put up here something divided by the period. In this case, it has to be negative 1 divided by the period, okay, to make it match. And then I'm going to say that's plus, factor out the e squared, times e to the I 2 pi. Again, some integer over the period. Here it's 2 over 2 t. Okay, we see those are equal, and we also see that now I've written it in a way that looks just like the synthesis equation for the Fourier series. So by inspection, I can just get the coefficients very simply. I can just say, yeah, let's use red. So I can just get that a of negative 1 equals 1. Negative 1 because that's what the integer is in that exponential function. And a2 equals e squared. And all the other a's are 0. If this isn't clear, think about the fact that x of t, this is the synthesis equation, that equals the sum over all k, ak, e to the I 2 pi, k over t, t. And so all I've done is identified that this is the term for k equals negative 1, this is the term for k equals 2, and all the other a's are 0. Okay, so that's one way to have done the Fourier series. Now, notice that this could be represented with the Fourier transform as well. That's the point of what we've just been talking about. So if we want to not use the series and say, well, let's just use the Fourier transform, then we don't even actually have to look for the period like we did for the series. Remember, the Fourier series, you need both the period and the coefficients to fully describe everything. Well, we don't even have to explicitly identify the period to do the Fourier transform. We simply take these two terms and we use our formula that we have above. A complex exponential goes to a delta function, right? So this becomes delta of f plus a half. It's a minus negative a half, plus e squared delta of f minus 1. There's the Fourier transform for the same thing. Okay. Couple things to notice, as I've emphasized. We now can do periodic signals with the Fourier transform if we'd like, using delta functions. But maybe more importantly, you have to realize that to do this, you cannot always just plug in your form. You can't just always use the formulas. Let me go back to our derivation of these relationships. We said that a delta function in one domain is a complex exponential in the other. Okay. To verify this, what did we do? We plugged in the delta function into the integral. That's easy. But what if we wanted to verify it the opposite way? We could always, like take this second example. We have a complex exponential. We could plug that into the forward Fourier transform, right? We should get a delta function. Will that work? If you try it out, you'll be frustrated, because you'll plug this into the expression for the Fourier transform, and you won't know what to, you'll get values that don't really make sense. Okay? It won't integrate. You won't get an integral that works. You'll get infinities, and it'll seem to be infinite everywhere, or maybe not. It'll be a little confusing. Okay? That's because this delta function is cheating. We're cheating, but it's helping, but it's simplifying life. Because we're using the delta function, for example, we can think of everything as the continuous time Fourier transform. I haven't completely made that case, but maybe you can see the arguments starting to form. Okay? But to verify these relationships, we have to do it. We can only verify them one way. For example, in this one, we can verify it by plugging this into the forward Fourier transform. We can't verify it by plugging it into the inverse. And this one's the opposite. We can verify this by plugging it into the inverse, not plugging it into the forward expression. So if you want to use this, you actually have to do it by inspection. If you're trying to do, like our example here, yes, we were able to take a Fourier transform by just, breaking this into parts and using the relationship we know. We would not be able to do this Fourier transform by plugging it directly into the integral. Okay. So that's why I made this second point here. You can do this, but sometimes you have to do it by inspection. Okay. So let me complete the case for why these are all special cases of the Fourier, continuous time Fourier transform. All right. So first of all, let me show that you could represent discrete time signals as continuous time signals by use of the delta function. So suppose we wanted to, suppose we have some signal x of n, it's discrete time, right? And we want to define a continuous time signal that sort of represents this discrete time signal. Well, here's a very natural way to do it. We can define x of t to just be this expression, a sum of delta functions when I plot it, it will make complete sense what I'm doing. So we have some signal, x of n is some signal of n, right? And we're trying to make a signal of t that represents it. So let's say there's 0, 1, 2. All right. So let's just give a simple example. Suppose this signal looks like this. Okay, it's just a short-lived little signal, has values, let's say 1 and 2. All right, now, if we, what we can do, this expression here means that x of t is defined to be delta functions at these integers with height equal to the signal value. So here's our continuous time signal that we've defined. 0 everywhere else, and it just has delta functions at those 3 points. Okay, pretty straightforward. So just think of this as a conversion from a discrete time signal to a continuous time signal that represents it. All right. Now what happens, let's say, suppose then we always think of discrete time signals as these continuous time counterparts. Let's see let's compare the Fourier transforms of the two. So the Fourier transform of this continuous time signal is going to equal, by definition, this integral. But I'm going to plug in this, this what we defined x of t to be. Okay, now I'm just going to change the order of the sum and the integral. Bring x of n out, because it's not in the variable of integration. And lastly, let's apply sifting. Sifting says evaluate this function at t equals n. So we get sum over n, x of n. And here we get e to the negative I 2 pi fn. Voila. The Fourier transform of this is exactly the same as the discrete time Fourier transform of xn. So in other words, we had two different definitions. We had a definition for the continuous time Fourier transform and one for the discrete time Fourier transform. And now we see that actually they'd be the exact same. If you convert your discrete time signal into this continuous time signal, then they're going to give the exact same Fourier transform. Okay, so there's sort of an equivalence there. So this is the argument. I'm making the argument here why, even though we have a different formula for discrete time and continuous time, if we think of everything as continuous time, we'll be okay. All right. Same thing would work for the Fourier series. You could do the same derivation. Okay. So let's now continue the argument of how why can we think of everything as a Fourier transform rather than a Fourier series. We've already kind of done that by example, but let's do it more generally. All right. Suppose we have period t and some coefficients. So we've got some periodic function with some Fourier series coefficients, right? Now we already said that Fourier series we can interpret as frequency domain components. So early on in the lectures we said, well, each of these coefficients corresponds to a given frequency. That frequency is 1 over cap t, 2 over cap t, all multiples of the fundamental frequency. Okay, and we said that we could think about the frequency domain components as being these coefficients of the Fourier series are like values that correspond to these different frequencies. So this was the frequency domain representation of these Fourier series coefficients. Okay. So let's just define a function of f using delta functions that would be that would correspond to this. So we could say, let's let x of f equal sum k, ak delta. Okay, so this is just exactly taking this frequency domain representation and representing it as a series of delta functions. We'll call this x of f. And let's see if this corresponds to, now what I want to argue is this is a Fourier transform of our signal. Okay, how do we check that? Well, let's look at f inverse. Let's look at the inverse Fourier transform of this that we just defined. Of course, the inverse Fourier transform it's going to be negative infinity to infinity. Well, it depends. Are we? I guess I didn't specify. Are we in discrete time or continuous time? Let's just say we're in. Let's say we're in continuous time. Okay. Remember that affects the limits of the integral. Plug this in. And then we have e to the negative I, e to the positive I. Okay, and then we just change the order again, sum over k, ak, and we're just going to, and we're going to now do the integral in here. And we evaluate that integral using sifting. And we say that's sum over k, ak, e to the I, 2 pi, k over t, f, or no, t. And that is exactly x of t by definition of the Fourier series. So what we've said is, look, if these are the Fourier series coefficients, then we know that this sum gives us back x of t. Well, if you interpret these, if you define an x of f in the most natural way here, then this is the Fourier transform of our signal, of our periodic signal. Okay. So again, the series and the transform are related in this way. So I guess the main point here is if you understand the Fourier, so these properties are going to correspond between the different Fourier transforms and Fourier series. If you understand the continuous time Fourier transform properties very well, then you're also going to be able to understand the properties of the other ones. They'll be basically the same. Sometimes there will be slight differences, which I try to emphasize. Okay. So let's see. I have time to do the ideal low-pass filter, and then we will continue. We'll talk about some more. We'll finish up talking about some properties of the Fourier transform in the next lecture that we haven't talked about yet. So last time I said because we have a convolution property of the Fourier transform, then convolution can be interpreted as filtering in the frequency domain, because you're just multiplying in the frequency domain. And there's ways of interpreting that as a filter. We looked at a couple examples. Here's one of the most well-known examples of a filter. It's the ideal low-pass filter. So in the frequency domain, an ideal low-pass filter is the following. It just is 0 everywhere except within some range that is specified by a cutoff frequency fc. Within that range, it's 1, 0 everywhere else. So mathematically, we can say h of f equals a rect with width. The width is 2fc. Okay, of this rect. So there's an ideal low-pass filter. The way it will affect a signal suppose you have an input signal here. Suppose you have something like this. Okay, that's our XF. This is the Fourier transform of the signal going into our low-pass filter. Then what comes out is this thing gets cut off at these frequencies, and that part disappears. That part's, I guess I should shade in the middle. So this part is the only thing that remains on the output of our low-pass filter. Everything else goes to 0. All right, we get rid of high frequencies. Okay, so now, what does this do in the time domain? Remember, it's going to be a convolution in the time domain because it's a multiplication in frequency. But what is the signal that you're convolving with? All right, well, we just do the inverse Fourier transform. H of t should be the inverse Fourier transform of that rect. Again, we use the time scaling property to find that that equals 2fc sinc of 2fc t. All right, so the bottom line is it's a convolution with this wonderful sinc function. So when you convolve with the sinc function, you're doing an ideal low-pass filter. Again, I can draw the sinc function. Here's t. Here's 0. Here's 1 over 2fc, 2 over 2fc, so forth. And the sinc function has height 2fc, and it goes like this. Okay, there's our sinc function. So you're actually convolving with this sinc function when you do an ideal low-pass filter. So some things to realize here. Of course, we can think of h of t as the weights of a local weighting, because that's what convolution is. So this is a local averaging, but rather than doing the maybe you would call it naive local averaging, where you just take some window and take an average, here it's saying, oh, if you really want an ideal low-pass filter, then you should weight the things that occur close in time by the most, but you should weight it in this weird way. Things that occur this long ago, okay, between 1 over 2fc and 2 over 2fc, you actually have a negative weight on those things for your weighted average. Okay. Now, even though this is called an ideal low-pass filter, that doesn't mean it's ideal for signal processing in all cases. In fact, often it's not. Because there's some properties we don't necessarily love about it. It's notice that to calculate the output at any one point, think of this as a smoother. To calculate the output, the input at times very far away are influencing the output. So what happens at one point in time still influences the output for a long time. Okay, that's known as ringing. It says if you have something occur, like a jump in your input, it's going to affect the output for a long time because of this convolution with sinc. Actually, forever. It's going to die off slowly and cause this ringing effect. That's often not desirable. So even though it's an ideal low-pass filter, it's not always an ideal tool for signal processing. It's not very localized in time. And, yeah. Okay. Thanks.